Approximately 62 light-years from Earth, in the constellation Serpens, there is a small orange star you have never heard of. It is not particularly bright. It is not particularly massive. It is roughly 60% the mass of our Sun and emits only about 3% of our Sun's light. It is a K-type dwarf, a class that makes up about 13% of the stars in our galaxy. There are millions of stars like it. This one is going to arrive. The star is called Gliese 710. It was flagged in the early 1990s when astronomers working out the trajectories of nearby stars noticed that one of them was aimed unusually close to us. Then, Gaia, the European Space Agency's stellar mapping mission, measured the sky properly, and every data release has tightened the prediction rather than loosening it. Gaia's first release put the encounter at 0.062 parsecs. The second release pulled it into 0.054. The third nudged it closer still. Here is what those numbers mean. In roughly 1.28 million years, Gliese 710 will make its closest approach to the Sun, passing about 0.176 light-years away, around 11,000 astronomical units. There is a 95% probability that it comes closer than 17,000 astronomical units. To put that in context, the nearest star to us today, Proxima Centauri, sits 4.2 light-years out. Gliese 710 will be more than 20 times closer than that. This will be the closest stellar approach in human history, in the history of mammals, in the history of vertebrate life, and arguably in the history of multicellular organisms on this planet. The last time anything passed this close to the Sun was roughly 70,000 years ago, when a small red dwarf called Schultz's star, combined with its brown dwarf companion, passed about 0.8 light-years away. That was a much more distant encounter than what Gliese 710 will deliver, and it left no detectable trace on our solar system. Gliese 710 will not be so easily ignored. At 11,000 astronomical units, the star will pass through the outer Oort cloud, the diffuse cloud of comets ranging from roughly 2,000 to 100,000 astronomical units from the Sun, that contains the reservoir of all long-period comets that ever enter the inner solar system. The Oort cloud is held in place by the Sun's gravity, but the gravitational binding is weak. A star passing through the cloud will disturb it. The question is how much and what happens next. When Gliese 710 reaches its closest approach, its gravitational influence on the outer regions of the Oort cloud will exceed the Sun's. For a brief period, a few 100,000 years, the orbital dynamics of trillions of cometary bodies will be perturbed. Most will be deflected only slightly. Their orbits will shift, but they will remain bound to the Sun. A small fraction, however, will be deflected inward, onto trajectories that bring them into the inner solar system. And here's where it gets worse. The Oort cloud is not a shell of debris sitting quietly at the edge of the map. It is the reservoir that every long-period comet in our sky has ever come from. Disturbing it does not damage the outer solar system. It aims it inward. The simulation work on this scenario has been ongoing since the early 2000s. The best current estimates suggest that Gliese 710's flyby will increase the rate of long-period comet entry into the inner solar system by a factor of about 10 for a period of roughly 2 million years following the encounter. During that interval, instead of seeing approximately 1 new long-period comet per year, the inner solar system would see 10 per year. Over the duration of the perturbation, somewhere between 10 and 20 million additional long-period comets would pass through the inner solar system. Most of those comets would pose no threat to Earth. The probability of any single comet impacting Earth on any given pass through the inner solar system is extremely low, on the order of 1 in a billion. But 10 million additional comets increase the probability proportionally. The chance of at least one of them impacting Earth during the perturbation period is roughly 1 in 100. Small, but not negligible. The size of the impactor matters. Most long-period comets are small, a few kilometers across at most. A comet impact of that size, while regionally catastrophic, would not be globally extinction level. The mass extinction caused by the Chicxulub impactor 66 million years ago was caused by an object roughly 10 to 15 kilometers across. Comets that large are uncommon in the Oort cloud, but they are not absent. The probability that one of the additional comets perturbed by Gliese 710 will be both large and on an Earth-intersecting trajectory is, using current modeling, somewhere between 1 in 1,000 and 1 in 10,000. Those are not zero, they are not negligible, but they are also distant enough in time and uncertain enough in detail that no responsible scientist treats them as a threat that anyone alive today needs to act on. The encounter happens 1.28 million years from now. Modern humans have existed for about 300,000 years. The encounter is in a future so distant that the species walking the Earth at that time may not be human at all. But the encounter will happen. The trajectory is locked in. The math says so. For any observer who witnesses the closest approach of Gliese 710, the experience would be unlike anything in known human astronomical history. Today, the brightest star in our night sky, after the Sun, is Sirius. Sirius is bright because it is intrinsically luminous and because it is close, about 8.6 light-years away. Sirius shines at magnitude -1.46 in our sky. The full moon, by contrast, is magnitude -13. At its closest approach, Gliese 710 will be at apparent magnitude -3. That is roughly 4 times brighter than Sirius is today. It will be visible during the day. It will cast shadows at night. It will be, by a substantial margin, the brightest stellar object in the history of our planet, excepting the Sun itself. It will also stay bright. Unlike a transient supernova or a passing comet, Gliese 710 will remain near its peak brightness for a period of approximately 10,000 years on either side of closest approach. Multiple generations of whatever species exists on Earth at that time will look up and see every clear night a star bright enough to read by. The star will not change visibly during a human lifetime. The angular motion of Gliese 710 across our sky during the closest approach will be approximately 3 arc-minutes per year, about 1/10 of the diameter of the full moon. A single observer would notice no movement at all, but over centuries, the star would slowly drift across the heavens, moving against the background of the more distant stars, in a way that would be impossible to ignore for any culture with even modest astronomical record-keeping. If life is still present, and if civilization is still functioning, the encounter with Gliese 710 will be the most significant astronomical event in the history of that civilization. It will be visible, it will be measurable, it will be predictable centuries in advance to anyone with the right tools. And the comets that begin to flood the inner solar system as a result of the encounter will be a permanent feature of the sky for tens of thousands of years afterward. We are at the very beginning of an encounter that we already know will happen. The trajectory has been measured, the timing has been calculated, the aftermath has been simulated. We simply will not be the ones to witness it. Our distant descendants might.